he received his PhD from Scuola Sant'Anna and worked as a postdoc for Silvestro Micera at École Polytechnique Fédérale de Lausanne in Switzerland, before making two important steps in his career, co-founding Sensars Neuroprosthetics in 2014, which is a company that develops neuroprosthetic systems for amputees. We will meet on Thursday his partner in crime, Dr. Petrini, on the industry panel. He is an Eastern European biomedical engineer. Why his origins are important, you might ask? Well, he is part of the kind of specific breed of scientists who know that everything in our field has already been done sometimes between the late 60s and the mid 90s. He develops devices with which interface the environment with the residual nervous system with a strong computational modeling component. And he was appointed professor at ETH Zurich in 2018. He is also, as I said, on the scientific committee of Neuroprosthetic Summer School, which means that he is transversally, fully, and solely responsible for the quality of his own talk. Thank you very much, Tani, and the mic is yours.
Thank you very much, Marco. So you hopefully see my screen. Non mi si sente? Sì, I guess. So I would start by agreeing with Marco that everything what we are trying to do there today is maybe eventually done in 1912 by Sherrington and company, but we are trying to reinvent the wheel maybe with a little bit more fancy ways. Once said that, I would be very glad to introduce you with our long-term research, which, as Marco correctly pointed, is taking its basis on a mechanistic understanding of what happens in a nervous system of humans once we stimulate them, and to connect that to the link of the translation. So to do so, please give me a second to share with you what is my and our research philosophy. So as said, we are starting from a deep understanding of a system, which is based on the combination of different knowledges that have been accumulated by the humankind. And basically, we do that through the computational models, which are basically able to predict how to transfer this into the design of optimal devices. As a second step, we do construct these devices, and in this case, it is a really foot of our PhD student with a system and real-time GUI that we developed for the clinical testing. And as a last but very important test, we do participate in clinical validation. So we are highly transversal. So we go into the clinics, we test our systems. And now there is a step which is often underestimated, which is the last step of this framework, which is the one where we take the results of our clinical validations and we return back to better understand our system. And I strongly do believe that that's the unique way to pursue the better knowledge and the wealth of humankind. So, since the topic of this talk is mainly about amputees and diabetics, I would first introduce what are the present possibilities for amputees in clinics around the world. So if you are lucky enough that the amputation happened close to some very well-equipped hospitals, so having cardiosurgery, normal surgery, orthopedic surgery, and maybe the amputation is not a product of the tiger who bite the hand or the leg, then there is a possibility of reimplantation. And of course, there is a problem with the time constraint for that action, and that amputated part can be destroyed. Other very promising solution that arose in 80s was a transplantation. And after the starting enthusiasm, which was very wide, we realized that there are several problems with these approaches. Among all, the fact that these persons, they need to take the immunosuppressors, which after a while are making the problems to their interior organs, especially kidney. And often underestimated problem is the one of the psychological acceptance. So many of these patients would refer that they would feel very strange because the dead person's body is touching them, while instead that would be his or her husband or wife. And so recently in Rehabilitation Institute of Chicago, the muscular reinnervation has been proposed by Kuiken and a team, and it is a very elegant solution, one of the best yet today for the very proximal amputees, in which we do take the residual nerves and we replant them through the muscular structures that are yet available. After several months, the nerves would naturally regrow within these muscles. And for instance, in this case, the user would imagine moving the hand and the chest muscles are going to contract. We can take this information through the superficial electrodes and move the artificial devices like prostheses. Of course, also this approach has some issues, as the one that in order to sense the information while we are decoding the movements of the user, we must stimulate tactile-wise the same area, and that is so-called sensory gating issue, which yet has to be solved. So where are we today, and where is our work placed? So we are in a site where, indeed, this is a seminal work from Pasquina Group and Walter Reed Hospital, where these tiny things are implants into the muscles. And whenever the user is imagining moving any of the fingers, these implants would reliably transmit through the wireless connection the signal to the coil, and then the proportional movement of the prosthesis would occur. So that would be an eventual solution for the motor problem. But on the sensory side, we could also go deep into the nerves, as this approach that has been developed in Cleveland by Professor Tyler and a group, where they do stimulate the residual nerves and give back the sensations from the missing hand. So of course, our dream is to make the bionic solution, which is combining two of these, and which is user the opportunity to move the robotic device and to feel what the device is doing meanwhile. So today we do have sophisticated robotic devices. So we are from this to that level regarding their sophisticated level, but as a functionality, you wouldn't believe, but we are much closer to the left part, because even if we have incredibly dexterous hands, arms, or legs, these are not well integrated with the nervous system of the users. And therefore, we must work hard in order to increase the functionality of those, both through the better control, but also to the better sensing of these devices. And indeed, my talk here is mainly on the sensory neuroprosthetic part. So the first question is, what do you believe? Are the upper or lower limb amputees clinically more relevant? And so even if the hand is much more fascinated from even the brain perspective, the reality is that in United States, in Europe, the number of lower limb amputees is more than 4 times numerous with respect to the upper limb amputees. On the other side, the nerves that we are trying to interface, and these are pretty much the realistic proportion, one is the arm nerve and the other is the nerve of the leg, are much different. So our neurotechnological means have to be very much optimized to one with respect to other. When we work with amputees, this is our upper limb amputee clinical study with Fernando, we can have many crazy cables hanging around. But when we go into the lower limb amputees, we do need a robust wireless communication in order to be able to execute these experiments. And last but not the least, when the clinical translation is done in lower limb amputees, whenever our prosthetic device falls, we can make serious injuries to our users. While in upper limb prosthetic experiments, basically we can lose few glasses. So it's a quite responsible task. And indeed, to achieve that, we first ask ourselves, what are the problems of lower limb amputees with the sensory feedback clock in everyday life? So as you can see here, they are very inconfident while walking, quite slow, and eventually they're suffering the possibility of very dangerous falls, as the one in the picture. And on the other side, since they do not believe to their prosthetic device properly, they're having highly asymmetric walking, which in the long run is having several problems, among which the development of the bone diseases and heart diseases. Finally, vast majority of those is suffering.
It's horrific pain. It's pain like, the best way, it feels like a tractor trailer has run over your leg.
Are suffering the phantom limb pain, which is presently poorly tractable with the drug medications. And that is also possibly due to the altered or irregular sensory drive from the periphery. So our way to work with these disabilities is to interface the residual nervous system. And in these pictures, many of approaches are presented. And in the present presentation, I'm going to speak mainly about the time electrodes and their implants in the lower limb of amputees. And these can be used both for the restoration of sensory motor function, for the pain management, but also, as I said, for bidirectional control of artificial limbs. So let's start from the physical basis of it. So how do we interact indeed with the nervous system? So the nerves and their ionic currents and devices that are having electronic currents are sharing the same language, which is one of the electrical field. And we can invent and design the neural electrodes to provide stimuli that would stimulate either axons or cells. And indeed, some already 10 years ago, together with my friend and collaborator Marco Capogrosso, today professor in Pittsburgh, we started doing something about this. So we asked ourselves, can we make something like this in silico? So what we basically did is to transfer what is known in neurophysiology into the programmed neurons in a neuron programming language, and we were able to program in silico different possibilities for the nerve population within single or multiple fascicle, and therefore we were able to estimate what would happen in different cases of neurostimulation. And so very briefly, that process works that we start from histologies. In this case, this is a vagus nerve histology perchance. Then we segmentate those pictures, we mesh them, we make a volumetric solutions of the voltages within the space. And then on the other side, in a neuron model, we import these voltages in order to solve the cable equations and to understand which of neurons would spike at which moment and for which current. That framework enabled us to design the devices which are optimal for both for the upper and the lower limb amputees, and to exploit that in their use. Of course, this seems like a nice pictures on the screen, but in reality, we did also extensive animal tracing and animal stimulation in order to see if the physical constraints of the models that we've been using make sense, and indeed, they are reasonably valid. So, what is our main goal with this stimulation? So what I've been explaining 1 second ago is mainly the part above. So you can have a nerve and electrode electrical model, understand the realistic fibers distribution, and understand and estimate with respect to different devices how many cells would spike in which way. But that's only one part of the story. On the other side, we have a mechanoreceptors, which in reality would elicit the physiological neurons spiking. And what do we want to do on the long run is to make these two symphonies, the spiking in the reality with a model which we call receptor neuron model. And indeed, today will be a student talk explaining much more about it, together with the classical hybrid fem neuron models into the optimal encoding algorithms, which would be the most efficient way to stimulate our users. And so among many things that models can help about is the one that is often asked from the surgeons while we are preparing our neuroprosthetic devices. For instance, how many electrodes should be implanted in a single nerve? And just to give you an example, this is an example of a human realistic nerve in which we are able in model to implant 1, 2, 3, or arbitrary number of different electrodes, and to understand how selective are we with respect to the different fascicles. Of course, we want to be selective as much as possible to many fascicles possible, because in that way we can restore the majority of functions. And when this thing has been translated into the reality, this is a real tibial nerve that has been implanted by our neurosurgeon, guiding the rules given by models. So this is a nice concept, but how did we go then to the reality? Indeed, we had 3 subjects with above knee amputation and strong phantom pain or fear of failing, and we performed the long-term clinical testing. And it has been, of course, an interdisciplinary, multi-center approach between different research and companies. And what is our solution? So this is the walking of an amputee without our intervention, highly asymmetrical and slow. So we provide them with a sensorized insole, which is transmitting in real time, together with the knee encoders, the informations about walking to the system controller. At its turn, the system controller is triggering the stimulation of the nerve transversally, and through the smart algorithms that we programmed for years, we are able to restore close to natural sensations from a missing foot and lower leg. And then the user can adjust his or her walking in a proper way. Therefore, presumably, they could observe several benefits. So the first step to do in this process is to calibrate the device. It means that for several days after the implantation, we are stimulating through different active sites of the electrode with different amplitudes and frequencies, and we are recording the answers from our users. As you can see here, there are 3 subjects, 3 transfemoral amputees that were reporting a vast number of sensations of different modalities. The thing to be really observed is the white area, which is corresponding to the electricity. That is often underestimated in neuroprosthetic field, but I want to exalt the importance of it because we can have up to half of sensation which are of electrical type. And indeed, today, Professor Benzmaya would speak a little bit about how to make more biomimetic stimulation algorithms in order to avoid this electricity issue. And so, since a while, I was wondering how is the best way to represent to somebody who is not from the field this neuroprosthetic approach. And so these are the steps that we do. First, of course, through the mapping graphical user interface, we have the set of sensations, which is elicited repeatedly. Then we would map the number of this sensation with respect to the positions of the electrode active site that are corresponding to the sensors of our sensorized insole and to the encoder closure. For the encoder closure, we have chosen the gastrocnemius medialis muscle, which would indeed contract proportionally to the knee movement. And then the rest is electrical engineering, in which we do connect our artificial sensors to the system in real time, meaning with unperceivable delay for the user. And then we are able, whenever the user walks, to transmit them back the proper neurophysiologically plausible sensation from the missing foot and the knee. So how does it work in reality?
Osjećam ovdje. Ne osjećam ništa. Osjećam ovdje. Osjećam ovdje.
As you can see, the user is able to recognize the different position, together also with placebo trials, from the wirelessly controlled prosthetic leg, which is, through the cables you can see on a bed, being connected to the residual, to his residual nervous system. So the next question which can be done is, how long after the implantation does it take for them to learn these new sensations? As I said during the calibration, since we have a number of different modalities of sensation, ranging from the vibration, pressure, touch, until the electricity, we can purposely choose those which are most comfortable to the user, because those would be mostly accepted and easy to use from them. So basically, the user you're going to see in a video has been the first time on his bionic leg since like 5 minutes, and these are his reportings.
Što osjećaš? Peta sa strane tu. Peta strana tu. Peta sa strane tu.
Dobro.
Ajde sad slobodno iskodaj kad njema nekoliko koraka opušteno, nemoj se plaćaš. Što? Je li prijatno to? Opušteno, kao da udaraš. Sad osjećam ko da moja noga. Osjećaš kao da tvoja noga? Odlično. Kao moja noga, ovo moram ništa više ne osjećam, ništa ne osjećam.
So these are really the personal statements from a user after a few minutes after the first fitting of the prosthesis post-surgery. But can we measure that in reality? So we were very much dedicated to measure both their perceptions of the prosthetic device and also their brain transfer. So in order to measure their perception of the prosthetic devices being embodied into their body schema, we measure them through the classic embodiment measures, in which we both ask them questions and questionnaires, and we also ask them to define where would we place their phantom limb with respect to the pool that has been moved left and right. And in that way, we were able to understand also quantitatively how much would be the proprioceptive drift with respect to their perception, with and without the neuroprosthetic intervention. So what we finally observed is that the neuroprosthetic intervention is highly boosting their both subjective feeling, but also the objective measurement of the artificial leg placement. So the embodiment has been boosted only when the full sensory feedback has been restored. And then, in order to measure what I've been saying 1 second ago, we also asked users, how do they feel about that?
When examiner is touching per upper foot with the sensors, and I feel the same place I feel touching on my leg. when he's touching my tongue or heel or foot anywhere. So I feel every time I feel where is he is touching the rubber foot. It was very interesting, like my own leg. First time I feel my leg, I feel my foot.
He is a transfemoral amputee, 6 years post-amputation, if I remember well. So it was quite impressive what we observed. But of course, also for this task of their personal feelings, we ask ourselves, but what happens in the brain? So we engineered a paradigm during which we did a dual task with users, which were having these headphones and a highly selective mobile EEG low noise. And in these, they were instructed to count the tones of high or low value while walking with and without sensory intervention. You have two users' results. And what appeared is that whenever they were provided with the sensory neuroprosthesis, their level of the mental layover, mental budget residual was very similar as in the case in which they were only sitting. While in a case when they were supposed to count those toes, so to be concentrated in doing so, and walk, which is the black line, their mental budget was completely absent. In reality, what does it mean? It means that in a case that of neuroprosthetic intervention, they would feel much less brain load. And for instance, they would make a difficult calculation if you would ask them, while in the other case, they would hardly listen to you whenever you ask them a question because it's a hard task. So after also understanding that this was happening on a brain level and all of these tests in the laboratory, we stepped out. And so we stepped out from the laboratory into the ecological environments. So in this task, which is really hard for prosthetic, especially transfemoral users, the subject is walking in the beach volley field, so very, very deep sand. And what they would report in the case of the neuroprosthesis of that they are constantly afraid to lose their neuroprosthesis because it's connected with a socket, and they do not know when to push, which is contrary to the case of the neuroprosthetic intervention. So due to the fact that we were restoring realistic sensory feedback, they were able to be more confident to push strongly, which has been also quantified, and therefore to have a higher mobility. And higher mobility is one of the strongest indicator of the wealth of some neuroprosthetic intervention in a lower limb amputees. As a second thing, I've been mentioning that they have a heart problem and that they have a wrong cardiovascular expenditure due to the prosthetic use. So we measure that as well. And in both user, in outdoor walking, we have observed that in a classical 6-minute walking test, they had a net volume of oxygen consumption diminished in a significant way, which gives hopes that we on a long run can diminish the number of heart attack in these type of users, which is 200 more likelihood with respect to non-amputees. Last, I've been mentioning that these users were experiencing a strong phantom limb pain. So in a different type of functioning of our device, which we call a neuro pacemaker device, they were connected to our stimulating system, and we've been providing them with the different types of stimuli and also, of course, the placebos. And what appeared in both users that have been supposed to this therapy is that with respect to the values of both MPCI and VAS scale, pre-implant and post-implant, during the pain therapy, they experienced almost complete or complete pain diminishment. We also tested different types of algorithms for the stimulation, but we did not observe the winning one. So we would further explore on that side and understand better, is it due to the somatotopic type of the stimulation or the type of stimuli that has been given during the trials. And then as a next step, starting from this very nice implantable result, we ask ourselves, can we make a system that could be easier for everyday use and maybe industrially exploitable? Together with Giacomo Valle and a project from Swiss, we started developing a system which has been tested in collaboration with the Balgris Hospital. And basically that system is made from a CE-marked components and superficial stimulators that are of course giving a remapped sensory feedback to the users. And in these, we've been measuring similar type of outcomes as the one with the implantable users. Interestingly, this is the real everyday use of that device with several amputees that participated in this non-invasive trial. Indeed, we are participating in a Cybathlon 2020 with such a device, and our user, which is a common manager, was able to win in a preparatory race against the third place from Osur, who was a Paralympic silver medal. So starting from there, we asked ourselves, could we exploit similar neuroprosthetic device for the wider population of users? And so we have observed that diabetics have similar important issues. Due to the very complex metabolic processes, they are losing the protective pain in their mechanoreceptors of the foot. So even the small rock can be unobserved while they are walking, which could cause in the long run the ulcers formation in a very big number of cases, also the amputation with the fatal outcomes. At the same time, many of them would report neuropathic pain, which is very similar in its nature and reporting to the one which has been reported from the phantom limb pain users. And so what you can see here is a walking, very insecure walking of the person with diabetic neuropathy and not an amputee. And so we do want to test a novel type of multimodal treatment for these type of users, in which we would combine the periphery and central effects of our approach, in which in periphery we would go with the tense approach to stimulate proximally to the foot the nerves in order to feel them back, the foot sole and the dorsum, and while we would provide them also with the virtual reality in order to treat the central part, the central piece of this pain syndrome. Their combination, called multimodal, is assumed to be a good measure for their long run treatment. Indeed, this evening there is a talk from Greta Beattoni tackling these issues. And so finally, with all of these results that I bombed you with, I just want to share you our deep conviction about the fact that we work hard both to restore the functionality, but also the happiness of our users, which is a very important factor.
Okay, man.
And all of this would be completely impossible without many of persons from my lab, like Natalie and Jelena, they're working on nerve modeling, Michele, Ariel, and Lauren that are engineering the wearables, and Francesco, who was, Giacomo and Greta, who are now in the lab. And all of these areas are clearly interdisciplinary and are pursuing us to work all together and very strongly in order to fulfill our dream of the future widespread transition of these technologies. With it, I'm thanking many of our collaborators, both from industry and hospitals, and I'm happy to take your questions.
Thank you very much, Stani. Actually, it's a very nice and smooth presentation. I think even the most general audience enjoyed a lot. And the person that is gonna take care of your questions today is Ariel Gabowski, who is a PhD student at Hofstra in New York. And she's also a panelist today. Ariel, you can go ahead.
Hi, Marco. Thank you, Stani. So we actually don't have any student questions, but I have a question. So in regards to the transverse intraneural stimulation, does that elicit neural responses that propagate afferently and efferently? And if so, does that difference in directionality have any difference in response? For example, if it's going afferently to the brain, does it potentially decrease any phantom limb pain?
So I'm not completely sure that I understood the question, but the answer is yes. You are, whenever you stimulate in some position in the nerve, you are doing both stimulation versus the nerve, but also versus the periphery. But in a case of our amputees, of course, the periphery is lacking, and so we do not have any problem with the motor responses. Also because in a tibial nerve, the muscles that you would imagine that would maybe contract are the ones that are amputated, so they're in the lower leg. And certainly we are only thinking about the afferent drive.
Marco, can I ask a question? Stani, you're working on a pretty much comprehensive approach to lower limb neuroprosthetics, but you're not touching at all the mechanics, right, of the prosthetic itself. Don't you feel that at some point this is actually a limit, like a significant limiting factor? Like in the mechanics of the lower limb neuroprosthetics don't even allow like so much of ankle movement, so that your feedback could be actually really be useful because of current limitations in the mechanics of the prosthesis.
Okay, I got it. I completely do agree. Indeed, our system is meant more for the systems in which we would have on disposal those sensors and those types of movements. But to be honest, there is, for instance, the power knee from Osur, and it's too complicated by the moment. They were, I hope nobody from Azure is listening, but I don't think they're happy users of this device, because in order to learn to use it, it would kind of push you through the stairs. I think we are very much on the rudimental level, and indeed that's going in line with what you were proposing yesterday regarding the neuromodulation. It's like we are stating a big things, and there are these beautiful companies around, maybe some on Thursday, aiming to, to do Star Wars job. But I think we are much more advanced on the side of actuators. We have many more problems on the sides of neurotechnology. We cannot decode high level, many degrees of freedom. Even in our sensory feedback, even if we have many positions where we go over five positions, maybe we can confound the user, etc. So I really do believe that our main work should be done on the side of neurotechnology, while we're already having very cool things in a mechatronic reality.
So we also have a question from Barang, if you would like to unmute yourself and ask one.
May I have a question?
Yep.
Yes. Javier?
Yeah, I think the video from Dr. Navarro froze. So
can you hear me now?
Yes, I can hear you.
Okay.
Yes, speak, Navarro, please.
no, unfortunately, it looks like the video is lagging, so we can't actually hear you.
Adele, I am not sure if I can take the questions I'm seeing here, because I see many questions.
No,
may I now? Can you hear me now?
Yes.
It's important, because if not, I will escape my talk later. Stanisa, regarding two mechanical questions. One is, how do you compare, or can you try to synergize what you are producing by nerve electrical stimulation, the tibial nerve, trying to emulate what the feelings from the foot are coming, from the mechanical pressure sensations that the prosthesis itself is making on the stump? I mean, most of the amputee people, lower amputee people, feel the amount of pressure or changes in the softness or in the hardness of the floor by the pressure that the prosthesis is making on the stump. So can you imagine a little bit synergistically using these two informations?
Yeah.
And the second also to mechanical, before my connection freezes again. What about osteointegration that has been, relied important in the upper limb? What about osteointegration for the lower limb in order to make the prosthesis more stable, stronger?
Okay, so regarding the first, thank you very much on questions. The first one, so I can tell you that among our users, we had one who was stating that he is able to recognize everything through the vibrations of his socket, okay? And so that's the type of person that we had to make a video of him being wrong in angles that we were giving to him. So this guy would say that he can understand where does he step and how much the knee of the prosthesis is closed through the socket. And of course, we did a trial without sensory feedback, closing the prosthesis on different levels, and he could not recognize any of those. And then he said it was just a trick, he could do it better next time. So of course, we did the falsification trials, and indeed, without neurofeedback, they would go under the chance level, and there is a supplementary figure in our paper showing that. While I do understand and I do believe that there could be synergistic use of both. That's what I do believe, because by the time these users get used to their socket and they learn many of those vibrations, the problem is that socket has to be often changed, and therefore also they have to relearn those sensations through the socket. But then we go to what you proposed, and which I do strongly believe that the future of all of these approaches is also integration, because that is much more elegant, comfortable for the user, and easy for them to feel.
So, Barang, if you'd like to unmute yourself and ask a question.
Yes, thank you very much. Thank you. It was a great talk. My concern was, you said that there might be another talk later on, but you said that the patients are feeling different sensations. And at some point you mentioned that you didn't explore, or you weren't able to change these sensations from one to another based on the frequencies. I was not sure about that. So basically my question is that, do you think trying something like the Bayesian optimization that Marco Bonizetto was talking yesterday, we could try to optimize the frequencies, the time dependencies, burst versus non-burst, or these sort of things, to change those pie charts that you showed from electric to other sensations, and if there is any intensity coding there as well, other than the actual modality coding?
Yeah, great question. Great question. I would start by saying that I would never imagine doing anything Bonizetto is able to do, because we simply don't understand it, but it works and we are unable. So said that, the question is great. So the pies are explaining the modalities, okay? But if you watch very carefully in these modalities, there are 56 active sites. And so 30% of them is giving electricity approximately, but the others are giving many useful sensations, and we need like 4 to 5 of them. So we have a redundancy of the sensations we need in order to implement our neuroprosthetic device. On the other side, regarding the modulation, we do a charge modulation, intensity encoding, which works very much properly. Somebody jumped in, yeah.
And then we also have a question from Us.
Yes, hi, great talk, thank you again. So my question is about reflexes. So since you restore the sensory feedback in your leg, do you keep the reflexes that you once had? And if so, does that mean that you have also nociception and like pain receptors restored too? Thank you.
Yeah, so regarding nociception and pain sensors, there is a lot of literature showing the fact that we can elicit the pain receptors, but we need much higher current. Indeed, today the talk of Professor Navarro would elucidate that. That's simply neurophysiology. So you need much more current to stimulate the smaller fibers. As one, regarding the reflexes, it was the second question. That was an interesting question we were asking ourselves, but I assume due to the fact that we are missing the end effectors, meaning the gastrocnemius, the tibialis, and the anterior muscle, we did not observe huge things happening, you know, on return, and I think that that would be the reason.
And then we have one more student question from Eunice.
Hi.
So,
my question is regarding the enhancement. So when we can provide a neuroprosthetic for an amputated leg for a patient, why we cannot enhance a normal leg or normal person, like give faster speed or?
Oh yeah, that's a great question. So my personal theory and ethics are against the enhancing of the persons. Honestly, there are many other books and thoughts about that, and of course it can be done. There are the projects worldwide that are working on a third hand, etc. But honestly, I'm more than happy we can restore the neurological disability to the users that are missing that. I think we can do a lot with our normal body.
Okay.
So then we have a few questions from the attendees in the audience. Why do you prefer a peripheral nerve stimulation approach instead of a dorsal root stimulation?
Great question. Dorsal. Okay, there is a recent paper, or maybe it's yet in preprint, about that. So simply, it's more selective what we are doing. It's more repeatable, and we don't have a problems regarding the areas that are being stimulated and the typology of paresthesia that is only being stimulated through the dorsal root, to the best of my knowledge. But of course, that's an interesting alternative, and I do assume that in future that could work also.
And then also, does the neuroprosthesis cause paresthesia?
Yeah, the neuroprosthesis does cause paresthesia. That's the part of the pies that we've been discussing before, the white part of the pies, and we want to avoid them. A patient mentioned that he felt anything about, no, he was mentioned that he didn't feel any pain. It was that the point, and he was feeling all as one continuum.
And then Benjamin T has a question about diabetics. So the skin tends to become a lot more fragile, and how do you overcome the problem as the interface to the prosthetic device is on the skin?
Yeah, an excellent question. So we do assume, and I would recall to make also the Professor Hoffman question, which is excellent indeed. Regarding this question of the skin, I completely do agree. The fact is that we go proximally with respect to the area that is being degenerated. So we want to play on the fact that the proximal nerve is yet healthy with respect to the periphery, and so to stimulate the area close to the ankle or even back to the knee in order to stimulate sensation in periphery which is being destroyed. So we do not go as the typical commercial system do under the foot or over foot where the area of the ulcers or the mechano destruction is already happening.
Did you want to ask her? Did you want to answer the other question?
Yeah, there is an excellent question, honestly, which is very neuroprosthetic school related from Ulrich Hoffman, professor. Thank you. So he asked, how long does the time implant last in nerves? And do we have histologies for that? And do we need an increase of stimulation amplitude to achieve the same effect? That's an excellent question. So the first thing about the time implant duration, in this study, we did 3 patients for 100 days because our main goal was not to establish how long these devices can work in a human being, but was to understand, and this is very important, does it make sense to implant these devices in this type of patients? Do we have some health benefits which tomorrow would force our reimbursement systems to pay for this and therefore to give it to the wide population of users? The first answer is yes. On the other side, we did a longer term study with amputees, upper limb amputees, Petrini et al. Annals 2019, where we have shown very decent stability over 6 months period. On the size of increased current, there is no, to best of my knowledge, any neuroprosthetic device that is not making paresthesia and it's not changing the thresholds over time. And since there are many students, that would be one of my take-home messages from this lecture, meaning that even the papers are often saying everything is perfect, wow, we work completely great. That is simply not true. Even the Argus system, which is the FDI certified system for the site restoration, which is using yet optical nerve stimulation, needs retuning of their threshold during the time. However, we were lucky that our threshold augmentation was happening during first several weeks and then established at the level of the charge that our electrodes could bear. Finally, the histology question, we do have histologies and they are presently under the processing. It appears that the answer, the fibrotic answer is happening only in the area of electrode while the proximal and distal area are clean. And that gives hope that macrophagic answer just only help to stabilize the electrode.
Okay, and then I guess we'll take one more question. So a few people were asking about the longevity of the stimulation and is there any data after a few years?
Okay, as I was mentioning a few seconds ago, the time electrodes were implanted up to 6 months and they were working properly. I can, however, give a good proxy from our animal study that we did with Sophie Wurt and Capogrosso in 2017, biomaterials, in which we have observed that in animals, we have 6 months of longevity in rats, which approximately would be transferred to 18 years of humans in very rough way. So I'm thinking that these electrodes, compared also to the cuff electrodes, which were recently implanted until 7 years, once that they are stabilized after 10 to 15 weeks, they would be able to make good stimulation to the human body. The problem is on the side of the cables, if the cables will resist for so long, because both hands and arms and legs are moving a lot. And what we observe is a breakage of some cables. And that is also underreported in the literature, but it is a very common problem of many neurotechnologies.
Thank you very much, Stanisa Raspopovic. Thank you, Ariel Gabowski, for the question and answer time.